Welcome back to the deep dive. If you've ever seen a rusty bridge, or maybe a pipeline with faded paint, or even just machinery left outside with that kind of flaking look, well, you've seen atmospheric corrosion. It's actually the most common way materials break down, and it's caused, believe it or not, just by the air around us. So today we want to go a bit deeper than just saying metal rusts. We're going to break down the specifics, like when it happens, where, and maybe most importantly, how fast. We're really diving into the technical side, the things that make one structure last for ages and another, well, fail really quickly.
Yeah, and our sources for this are pretty technical. They're guides that really define this type of damage, lay out the critical factors in the environment, the things that speed it up, you could say. And they also cover the advanced ways we look for this damage before it becomes a real problem. It's kind of a global roadmap for keeping assets intact.
And right off the bat, the thing that really jumps out is just how incredibly different the corrosion rate can be just based on where you are. I mean, you could literally go from what's called a very severe environment to one with very little corrosion just by traveling, a few hundred miles sometimes. It really hammers home that this isn't some uniform issue. It's intensely local.
That's absolutely the core idea. Corrosion isn't generic. It's super sensitive to the local conditions, and that sensitivity, it drives the whole strategy for how you deal with it.
Okay, so let's dig into that variability. Starting with the basics, what exactly are we talking about with atmospheric corrosion, and what materials get hit the hardest?
Fundamentally, it's corrosion that needs moisture from the atmosphere to get the electrochemical reaction started. That moisture could be rain, could be dew, fog, mist, even just high humidity.
Yeah.
But it has to be present. And the main victims, well, they're the materials we use most in infrastructure. Carbon steel, low alloy steels, and also copper alloyed aluminum. They're the workhorses, so they take the brunt.
Right. And you mentioned location dependence. To really grasp that, we need to look at the rates measured in MMP. That's mils per year, right? Thousandths of an inch.
Exactly, mils per year. And the range here is, well, it's pretty stark. If you're in a really corrosive marine spot, think constant salt spray. You might see metal loss around 20 molb. Even in heavy industrial zones with air full of sulfur compounds or acids, you're still looking at a dangerous rate, maybe 5 to 10 molb.
Okay, 20 mil/p. That sounds small numerically, but what does that actually mean for, say, a standard pipe with a quarter-inch wall?
That's where it gets serious. A quarter inch is 250 mils, losing 20 mils a year. Theoretically, that's only about 12 and a half years before it's gone completely. But in reality, corrosion is rarely perfectly even. Localized attack, pitting, means failure happens much sooner than that. Now, compare that to, say, a moderately corrosive inland place, maybe just dealing with normal rain and humidity. There, you're typically looking at maybe 1 to 3 molb.
Wow. Okay, so that pipe's life just jumped from maybe 10 years to potentially over 80 years just by moving it inland.
Pretty much, yeah. And then if you go to a really dry rural area,
Even lower.
typically less than 1 molp. So that massive swing, less than 1 to 20. That's why classifying the environment isn't just paperwork. It dictates everything. Inspection schedules, budgets, for decades.
Okay, so that sets the scale. Now let's get into the why. What are the factors actually driving that rate up from less than 1 to 20? This is section 2, the critical factors.
Right. So beyond just the physical location, which we've established is huge, and the presence of moisture, whether it's humidity, rain, mist, it's really the contaminants mixed in with that moisture. They're the chemical accelerators.
And what specific things in the air are we talking about, the main culprits?
We're looking at things like chlorides, think sea salt or de-icing salts. Then there are sulfur compounds, often from industrial pollution, H2S, and even fine particles like dirt or fly ash. But what's interesting is they don't all attack the metal in quite the same way.
What do you mean?
We'll take chlorides. They're really common in marine areas or where there's road salt. Chlorides are particularly nasty because they're small and they actively break down the natural protective layer, the passive film that forms on steel. They tend to cause very localized damage like pits. Sulfur compounds, though, often from burning fossil fuels when they mix with moisture. They can form weak acids like sulfuric or sulfurous acid. That tends to accelerate the general corrosion rate more evenly across the whole surface. It makes the whole environment more acidic.
Okay, so one causes deep, localized holes. The other causes more widespread thinning. That difference seems pretty important for how you'd inspect or repair it.
It absolutely is. And then we get to some factors that maybe feel a bit counterintuitive. The first one is temperature. We generally see corrosion rates increase as temperature goes up. but only up to a point, around 250 degrees Fahrenheit or 120 Celsius.
That part makes sense, right? Heat usually speeds up chemical reactions.
Exactly. But above that 250 F mark, surfaces are often too hot for a stable film of water to exist. So paradoxically, the high temperature can actually prevent corrosion because the surface stays dry.
Huh. So if it's hot enough, over 250 F, it's too dry to corrode. So why do we worry about inspecting hot insulated pipes then? Shouldn't they be safe?
Ah, and that's the catch. That's where we get corrosion under insulation, or CUI. That dry surface protection disappears. The second moisture finds a way under the insulation. The insulation then acts like a sponge, trapping that moisture right against the hot metal. It's hot enough to accelerate the corrosion reaction, but not quite hot enough to boil the water off instantly. In fact, studies often show the peak danger zone for CUI is often right in that, say, 140 degrees air to 250 degrees range.
So the very thing you put on for protection, the insulation, actually creates this hidden, highly corrosive little microenvironment.
Precisely. It's a classic hidden hazard. The protective measure hides the attack mechanism. And, while we're on weird factors, might as well mention biological input. It's usually not causing catastrophic failure like CUI, but things like bird droppings. They're acidic, they can cause definite localized corrosion, and some pretty unsightly stains on equipment. Just one of those things you deal with out in the field.
Huh. A very specific feathered form of chemical attack. Good to know.
But moving back to the engineering side, things like physical orientation and design are also really important. Which way a structure faces the wind and rain matters, sure, but often bad design choices matter more. Things that inherently trap water, like horizontal beams that don't drain well or crevices that aren't sealed properly. They create perfect spots for corrosion to take hold.
Which leads us nicely into Section 3. Where does this corrosion tend to hide? If location and temp are the drivers, where do people consistently find this damage or maybe miss it?
Well, any carbon or low-alloy steel equipment that's unpainted or uninsulated and operates below that 250F threshold is potentially vulnerable. Also, equipment that's downwind from known sources of contaminants, think cooling towers releasing mist or wet gas scrubbers, those are always high on the inspection list.
I usually picture big tanks or long pipelines, but the sources specifically mention piping resting on pipe supports. That seems like such a small detail.
Oh, it's a huge detail in practice.
Yeah.
Ask any maintenance engineer who spent time walking the lines. Pipe supports are notorious. You've got the load of the pipe, maybe some slight movement or vibration, and the support itself often creates a little trough, a crevice. It's almost guaranteed to collect water, dirt, debris. And once water gets trapped in that tight space, the oxygen gets used up locally, which sets up a condition for accelerated crevice corrosion. It can just chew right through the pipe wall there, much faster than the general corrosion happening elsewhere.
Okay, so it's another one of those hidden zones. And that hidden risk must also apply to equipment that's shut down, right? Idled equipment.
Absolutely. If a unit is shut down and just left sitting out there, it's constantly cycling through ambient temperatures, getting wet, drying out. It's very vulnerable, unless it's properly preserved or mothballed, as they say. And of course, you see major atmospheric corrosion on things like piers and docks in marine environments. They're kind of the poster children for this type of relentless attack.
When you actually find the damage, what does it look like typically? Is it always obvious?
Not always obvious how deep it is, but the appearance gives clues. It depends on whether moisture was trapped, and if there was a coating. The attack might be general, sort of widespread thinning, or it could be very localized pitting, especially if chlorides were involved or if water was trapped. Even if the actual metal loss isn't immediately visible, you'll almost always see that characteristic reddish-brown iron oxide scale, classic rust. And if there was a coating but it failed in one tiny spot, like a pinhole, that spot becomes a focal point for attack, and you can get rapid, deep pitting starting from that tiny defect.
And we should probably remember this isn't just about structural steel. Things like bimetallic connections, say, copper wiring bolted to an aluminum bus bar, those are also prone to atmospheric corrosion, right? It accelerates the galvanic reaction between the two different metals.
Yes, absolutely. The atmospheric moisture acts as the electrolyte, and the connection point corrodes much faster than either metal would on its own. It affects everything from thick steel plates down to tiny electrical contacts.
So, given all these ways things can corrode, how do we fight back? Section 4, prevention, and the high-tech inspection side of things, moving beyond just looking for rust.
Right. Well, the first line of defense, the most common one, is simply applying paints or coatings to equipment that would otherwise be unprotected. But, and this is critical, the sources really hammer this home. The effectiveness of that coating is almost entirely dependent on getting the surface preparation perfect. You have to get the steel absolutely clean, and then apply the coating correctly to the right thickness. A poorly done coating job, especially in a tough environment, it might look okay for a short while, but it provides almost no real long-term protection.
Okay, so good coatings are key, but once something is coated, or especially if it's insulated, just looking at it isn't enough. That's where the advanced inspection methods, the NDT, non-destructive testing, comes in, all those acronyms.
Exactly. We need ways to assess the condition without having to, cut it to the equipment.
Maybe we can break down those tools by what they actually do,
Yeah.
starting with visual.
Sure. So advanced visual testing, or VT, goes way beyond just using your eyes. We now use high-res cameras, mirrors for hard-to-reach spots, even things like laser scanning or structured white light imaging. Those can create detailed 3D maps of corroded surfaces, showing pit shapes and depths. And we still use basic tools like pit gauges to physically measure the depth of any visible pits.
Okay, that covers the surface. But what about seeing through the metal, measuring how much wall thickness is left?
That's primarily where ultrasonic testing, or UT, comes in. Basic straight beam UT sends sound waves in and measures the time it takes to bounce back, which tells us the thickness. But we have much more sophisticated UT techniques now, like shear wave UT, sub-UT, or phased array UT, PAUT. These can give really detailed maps of the inside of the metal, finding flaws and measuring thickness variations very accurately. And for checking long stretches of pipe quickly, there are screening techniques like EMAT, or guided wave testing, GWT. GWT sends a sound wave down the entire length of the pipe, allowing us to spot significant wall loss, potentially kilometers away from the sensor.
Kilometers? Wow, that's incredible range. What about X-rays? Does radiography play a role?
It does. Radiography, or RT, including newer digital and computed radiography, gives us an image kind of like a medical X-ray showing density changes. We often use specific RT techniques like profile RT, where you shoot through the side of a pipe to look for thinning or internal corrosion deposits.
Okay, so VT for surface, UT and RT for thickness and internal structure. But what about that really tricky one, finding corrosion hidden under thick insulation, the CUI problem? Standard UT needs contact with the metal, right? So how do you screen for that?
That is the perfect application for eddy current testing, or ECT, specifically a technique called pulsed eddy current, or PEC. PEC is fantastic for this because it works through the insulation and any weather jacketing. You don't need to strip it off. It uses electromagnetic pulses to induce eddy currents in the steel below. And by analyzing how those currents behave, it can estimate the average remaining wall thickness under the probe. It's mainly a screening tool. It tells you if there is significant loss in an area, but it lets you quickly scan large insulated areas and pinpoint spots that need further investigation, maybe by cutting plugs in the insulation for direct UT. It saves a massive amount of time and money compared to stripping insulation everywhere.
That ability, seeing through the insulation barrier like that, really shows how finding even common rust has become this, well, high-tech engineering challenge.
It really has. It's the cost of keeping critical infrastructure running safely in environments that are often actively trying to eat it away.
So wrapping this up for you, the listener, the big takeaway here seems to be that atmospheric corrosion, while common, is incredibly dependent on specific factors. Managing it isn't just about slapping on some paint. It takes really careful surface prep, smart design choices like avoiding those water traps and deploying some seriously advanced inspection tools like PEC, especially to find the damage that's hidden, sometimes intentionally, by things like insulation.
And maybe a final thought to leave you with, connecting back to that temperature paradox in design. The environment sets the potential corrosion rate, yes. But often, it's our own designs, the pipe support that traps water, the poorly sealed insulation seam, the spot that just doesn't drain right, that turn a manageable situation into a localized disaster zone. It highlights how the battle against corrosion often starts way back on the drawing board. The crucial question for an engineer maybe isn't just how corrosive is this environment, but how might my design choices accidentally create a tiny microenvironment where corrosion can run wild? Because that localized failure point, that's almost always the one that bites you.